Hey everybody, Trey here. Welcome back to another video. Back with another case study today, but we're going to switch it up a little bit. We've been covering these more prolific sort of tornado events in our case studies recently, and today we're going to cover an event that was forecast to be a prolific tornado outbreak, but fell pretty short of that mark, and that was the infamous May 20th, 2019 high risk across northwest Texas into Oklahoma. This was a very well forecast event. Several days out, there were signs that this had the possibility of being a very significant tornado outbreak. But some factors came together that kind of mitigated the overall risk. And thankfully for the people of Texas and Oklahoma, the overall degree of the severe weather outbreak was tempered by those factors. And of course, we'll get into those in this video. Before we get started, I want to just say something and clarify something right off the bat. I hear the word bust thrown around for this event and many other events that underperform. This was by no means a bust as far as severe weather goes. There were over 200 severe weather reports throughout the entirety of the event, almost 40 tornado reports as well. So from a severe weather perspective, this was by no means a bust. There were several damaging storms that impacted people's lives and property. The way that I look at it is it underperformed based on what was expected. The forecast was for a significant outbreak with multiple strong to violent long track tornadoes, and that didn't really happen. And even the title of this video, May 20th, 2019, what went wrong? Of course, it was a very good thing that we did not see the tornado outbreak that was forecast across Oklahoma and Texas, but it was definitely far from a bust of an event. People were impacted by these storms, but we're going to look at this video into why did this event underperform based on what was forecast and what was expected for this event. So with that out of the way, let's go ahead and get started here. Of course, I wanted to show this image. Everyone knows this image. This was the HRRR run from the morning of May 20th, 2019, showing an abundance of discrete tornadic supercells across the open warm sector, given an upper echelon parameter space. So, if you were anywhere on social media on that day, you saw an image like this that was pretty much painting an apocalyptic look for much of Oklahoma for this event. Of course, that didn't materialize, and we're going to look at why in this video. So let's go ahead and get started here. We'll start off with the meteorology, as we always do. We'll start off at 500 millibars, and the first thing that jumps off the page is this big old trough centered across the Great Basin region here. Very high amplitude, closed circulation here. That would open up as we went on through the day on the 20th. But overall, a very potent trough with a strong band of enhanced winds there rounding the base of that trough, encroaching into the southern plains vicinity. If we go up to 300 millibars, we can really see that divergence and diffluence aloft that we talk about. You can see the spreading apart of those wind vectors here approaching the Texas Panhandle into western Oklahoma. We've talked about this many times before. When this occurs in the upper levels of the atmosphere, it creates a void, and the atmosphere doesn't like to have that void. So what it does is it brings air up from below to fill that void, and that's how we get large-scale rising motion for the initiation of storms in a given environment. And you can see here as we go on through the day, very nice diffluence here moving into the Texas Panhandle, western Oklahoma region, right in there. Favorable, fairly subtle, but favorable large-scale, synoptic scale ascent, favorable for storm initiation in the warm sector across Texas and Oklahoma. We'll go down to 700 millibars here, and you can see a few different shortwaves rotating through. Some kinks in those height contours there. You can see a little bit of one maybe right in there, one back in here, one back in here. So numerous little shortwaves moving through the overall sort of long wave trough here. And we've talked about these shortwaves before. They act like little engines, little slightly they provide a slight enhancement in the ascent just out ahead of them, and you can get storm initiation from these shortwaves in kind of localized areas. And we saw a few of those rotate through here on the 20th. Let's go down to the surface and see what is going on. And this is at 12Z, so the morning of the 20th. Kind of a broad circulation here across eastern New Mexico there, with kind of a center down here near Roswell, and maybe one up here in southeast Colorado. If we take a look at our surface map here, kind of a closer in view, You can see a couple things right off the bat. Kind of, you see that circulation there in kind of southeast Colorado there. There is kind of within that kind of broader sort of cyclonic circulation there at the surface. So surface low centered somewhere in eastern New Mexico, southeast Colorado, with a warm front draped off to the east, generally toward the Dallas-Fort Worth area. You can see the northerly and easterly winds here to the north of that boundary. Would probably be somewhere sort of in this vicinity. It's a little bit difficult to tell. Somewhere probably right in here, draped out across the Dallas-Fort Worth area. You can see the temperature gradient there and a slight wind shift. Again, winds kind of out of the east-southeast to the north of the boundary. Winds out of the more out of the south-southeast to the south of that boundary. So a definite wind shift there. And this would be the warm front in place across the region. This was forecast to lift northward throughout the morning hours as we had a pretty significant mass response due to kind of continued cyclogenesis out here to the lee of the Rockies, thanks to that broad and strong 500 millibar flow out of the southwest, traversing the Rockies, and of course we get lee cyclogenesis to the east of the mountain range there. In this case, in southeast Colorado to eastern New Mexico. That would allow the warm front to lift northward and really start to pump this moisture northward into the region. We'll go back to our kind of broad view surface data here, and you can see what we have going on. A very broad reservoir of 70s dew points here, all the way up almost to the Red River here at this point, early in the morning. It's stretching all the way out to far west Texas there, so a very broad swath of 70s dew points there ready to be pulled northward into the warm sector as that warm front lifted northward throughout the morning hours. 850 millibars. We'll go ahead and look at our low-level jet that was in place on the morning of the 20th. You can see here what we've got going on, kind of a broad 850 millibar cyclone there, centered across that Great Basin region, with a broad area of low-level jet here across Texas and Oklahoma in the morning hours, 30, 40, 50 knots here, pumping that low-level moisture northward and really helping to push that warm front to the north, and that would continue throughout much of the day. We would see kind of that 40-knot low-level jet kind of sustain itself across the region throughout the day to both continue to pump that moisture northward and enhance the wind shear, especially in the low levels. And we'll take a look at some photographs here in a second, but a very potent environment was setting up, fairly obviously potent environment setting up here. This, of course, southeasterly winds at the surface as that warm front shifted northward. This is at 16Z, and you can see exactly where that warm front is. Much clearer wind shift here at this point, somewhere right in here, kind of right off in this vicinity, right in here. Winds to the out of the south-southeast to the south of that boundary, with kind of winds out of the northeast to the north of that boundary. So that warm air advection was really helping to push that warm front to the north throughout the morning hours and kind of set up a broad warm sector to the east of a dry line and south of that warm front there. We'll go forward in time here a little bit. This is at 18Z. We can pick out where that dry line is. You can see 50s dew points drastically dropping into the 30s out here in New Mexico, with 70s dew points out off to the east. So the dry line was somewhere kind of in this vicinity here, bending back toward the west there. And with our surface low, kind of broad sort of surface low up here in eastern New Mexico, dry line there, warm front draped across somewhere across Oklahoma in this vicinity, with again that very broad reservoir of very juicy low-level air. You can see already low 80s temperatures with mid-70s dew points out here. That's a recipe for a pretty significant severe weather event given the wind profile. Of course, south-southeasterly winds here at the surface, veering and increasing to southerly winds here at 850 millibars with southwesterly flow aloft. The shear profiles were pretty dang solid here for a significant severe weather outbreak. If we look at our soundings here, this is the Norman sounding from 12Z. You can already see that warm advection ongoing. The veering of those winds in the low levels was very favorable for that warm air advection that was ongoing. A little bit of an inversion here. Of course, we were just north of the front at this point at 12Z, 7 a.m. on the 20th there. So we were north of the front here at Norman, but that would soon change by 15Z. Much of the same, wind profiles increasing as you can see, but by 18Z, completely uncapped and ready to go here deep, deep moist layer up to 700 millibars here at Norman. We were pretty much completely uncapped by 18Z just after lunchtime here, and of course the wind profiles had drastically increased over that time. Strong low-level jet here, 1 kilometer winds at about 40 knots here, so very strong winds in the low levels atop kind of modest southeasterly surface winds. So long photographs favorable for supercells, and a very strong curvature there in the low levels with ample streamwise vorticity. Of course, we've talked about streamwise vorticity before. It's how our storm relative wind vector, which is drawn from our storm motion vector to the hodograph, relates to our horizontal vorticity vector, which is perpendicular to the shear vector, which is along the hodograph there. So, and when these two vectors are parallel to each other, that's when you have streamwise vorticity. Think of a football that's thrown. Think of an NFL quarterback throwing a football, that perfect spiral. That is what a storm is ingesting. And it doesn't take much when you have ample streamwise vorticity like this. That storm is ingesting those tubes of vorticity, those horizontal convective rolls that are rotating, very easily tilted into the vertical and stretched to become the rotation, eventually become the rotation within the supercell, and eventually the tornadic rotation in a supercell there. So streamwise vorticity aplenty here across central Oklahoma into northwest Texas here. Take a look at a couple more soundings from this event. We'll start off, we'll just look at our 12Z soundings here down at Dallas-Fort Worth. Much of the same, closer to the warm front there, so kind of right on the front here. You can already see some semblance of that moist layer there that would increase throughout the afternoon. A little bit of that elevated mixed layer, that capping inversion still remain there. Again, that EML is that layer of warm, dry air that exists out in the desert southwest near the surface that is sort of advected off to the east with those kind of low-level sort of southwesterly winds, low and mid-level southwesterly winds. So a little bit of that remnant EML there. And as that warm front lifted northward, we got surface heating and the approach of that trough to help erode that cap fully. Down here to the west, we were definitely fully in the warm sector, and this was a little bit more representative at the time. So the areas out to the west near Midland and Lubbock were already primed here as early as the morning hours, 7 a.m. here on May 20th. Moist layer extending up to about 740 millibars or so there. Elevated mixed layer, of course, in place there, had transported itself across from the desert southwest and the Mexican plateau across the region. We'll talk about that later as well. It became a factor later on in the day. But deep moist, nice layer of EML atop that deep moist layer, and profiles were already very much favorable for tornadic supercells this early in the morning, and this was just a preview of the environment that was to be advected across northwest Texas and central Oklahoma in the coming hours. So early on, we had storms fire quite early in the overnight hours. This is at just after 9Z here. So about 4 a.m. Central Daylight Time, we had storms fire in eastern New Mexico into the Texas Panhandle. These would become more numerous with time and spread off toward the northeast, and they would help just kind of retard the northward advance of that warm front. We recall at 12Z, it was somewhere kind of down in this vicinity here. It would begin to lift northward, but these storms would kind of help reinforce it somewhere across from northeast Oklahoma down through central and to western Oklahoma and northwest Texas. It would still advance northward, but again, that precipitation to the north would kind of retard the full northward retreat of that warm front. Still, again, plenty of that warm front, that warm sector would move northward into central Oklahoma to keep the forecast on track. These storms were a result of kind of that increasing forcing for ascent associated with the incoming trough, as well as warm advection, especially out here across central Oklahoma. We've talked about this before. Warm air advection, or WAA as it's colloquially called, is just the transport of warm air into a region. And of course we had warm, moist air down here across much of Texas, down into the Gulf that was being pulled northward on that low level, that's strengthening low-level flow. As that happens, and as it interacts with that warm frontal zone, and it will kind of overrun that warm frontal zone, and that can be enough lift to initiate storms on the cool side of the boundary. So these storms were fairly elevated initially. Of course, we saw the profiles favorable for supercells early on, although they would remain elevated. So the tornado threat was pretty much nil with these early storms. But we had a severe thunderstorm watch out for damaging winds and large hail with these storms. We had a few stronger cores within this early activity. But of course, the warm sector would remain pretty much clear of any convection throughout the morning and early afternoon hours before storms started to get going there, just ahead of the dry line there across the Texas South Plains, and that would move into northwest Texas. So if we go to our visible satellite here, we can get another sort of view. As we go through the morning hours, you can see that those low-level clouds streaming northward very rapidly on that strengthening low-level flow. That is a very good sign of warm air advection here. You can see the early storms to the north of that warm front, a very broad sort of complex of storms there in the morning hours. We go on through the morning hours as well, and I want you to keep an eye on the open warm sector out here. Let me try to get an image here that kind of shows this. This is a good one. So this is just after 11 a.m. Central Daylight Time here. Notice these low-level clouds are kind of organized in bands right here, and these were speculated to be horizontal convective rolls. The Storm Prediction Center issued their first MD for the event just before 11 a.m., highlighting this region in northwest Texas and the southern Texas Panhandle. And their next MD kind of pointed out these sort of horizontal convective rolls here. And these horizontal convective rolls, as we've discussed before, are just kind of, you can think of them as kind of rotating cylinders that are oriented horizontally along the ground. As you can see in kind of that visible satellite image, those kind of bands of clouds there. Those can provide enough lift and enhancement of the low-level shear along them to both initiate storms and help feed those updrafts with that nice sort of spinning football analogy that we use, that nice rotating air that can, as the updraft tilts and stretches these horizontal convective rolls, the storms themselves can start to rotate, and we can eventually get tornadic supercells from these. So there was great concern that the open warm sector, that these horizontal convective rolls would provide just enough confluence along them or convergence along them to promote enough forcing to promote storm development along them in the open warm sector, well ahead of the dry line, which was still well back here into the Texas Panhandle and Texas South Plains, and well to the south of the warm front, which was up here in central Oklahoma. So again, we've talked about this before, particularly in the May 3rd, 99 outbreak and a lot of our southeast outbreaks, that all you need is these little kind of horizontal convective rolls or confluence bands out well into the open warm sector to provide just enough subtle forcing for discrete supercell development along them in the open warm sector away from boundaries. And that was kind of the concern here, given this pretty significant environment that was already in place here, uncapped, very strong looking photographs there for tornadic supercells, that these horizontal convective rolls would be enough to promote discrete supercell development out in the open warm sector. And so, I was out chasing this day, and we were sitting out here in southwest Oklahoma, kind of waiting and watching for these horizontal convective rolls to blow up. But the first storms to fire were down well into, we're just ahead of the dry line again, out kind of in the Texas South Plains vicinity. You can see those early storms there. This is the Lubbock reflectivity, Lubbock radar reflectivity here. We go on with time, and we first get storms to initiate down here kind of east of the I-27 corridor there in the Texas South Plains, well, a little bit ahead of the dry line. So these were not purely dry line storms. The dry line was still a little bit farther back out here to the west. So these were out in the open warm sector and poised to move off toward the northwest into northwest Texas and southwest Oklahoma, where, of course, as we said, the environment was getting increasingly favorable for long-track tornadic supercells here. So these were the first storms to fire up out kind of in the open warm sector, and they pretty quickly kind of had that look to them. They kind of consolidated there. You can see multiple updrafts, and we kind of got sort of an increase in the reflectivity there, and kind of that one dominant cell to take over. Although these would start to pop as well, kind of out in the open warm sector, and we would get discrete storm development out of these. We also had a secondary kind of batch of storms here across central Oklahoma. So we'll start here early in the morning. We go on through the morning hours, and of course these are our warm advection showers right here, of course non-severe as we said, that warm air advection overrunning that warm front and providing enough lift for these elevated storms with the potential for hail and damaging winds on the north side of that warm front. We go on through the morning hours here, and you can see kind of an increase in this just sort of weak showery activity just to the south of that warm front. The warm front at this point was kind of somewhere across kind of that I-40 to 44 corridor there in central Oklahoma. So there was a general increase in kind of this showery activity to the south of that warm front. And you can kind of see even these horizontal convective rolls, these kind of bands of slightly enhanced reflectivity here in southern Oklahoma that were kind of the focus, the potential focus for that warm sector convective development. And we continue to get showers to develop kind of along, it appears maybe along them and out kind of in the open warm sector on that subtle forcing. And it was this band of showers here that developed across southwest Oklahoma, moving off toward the northeast, that was of particular concern, because there was one storm that kind of quickly developed supercell characteristics here. You can see the little bean shape with this storm right in here, moving off toward the northeast. And in this kind of environment, there was plenty of wind shear there for this to turn into a tornadic supercell. And that's exactly what it did early on. You can see the bean shape there, the very pronounced hook echo as it moved off toward the northwest of the Oklahoma City metro area. And this would be coupled with that storm in northwest Texas that continued to get going there. These were kind of maturing simultaneously here. You can see multiple discrete supercells developing out of this warm sector activity. Classic hook echo right here, you can see supercell here and a couple of different supercells up in here moving into the eastern Texas panhandle. So that was these kind of two areas there, central Oklahoma into northwest Texas as these moved off toward the northeast. This first storm in Texas near Paducah would produce a tornado, a very brief tornado, as would the storm that moved toward the northwest of the Oklahoma City metro area. This is some footage of the Paducah, Texas tornado there. Very brief, very small tornado, but we thought this was kind of a precursor of what was to come as these discrete supercells moved into southwest Oklahoma. This was some footage from the Kingfisher to Crescent, Oklahoma areas. That central Oklahoma supercell interacted with that warm front and actually produced twin tornadoes that occurred simultaneously to the northwest and north of the Oklahoma City metro area there. So this looked like it was going to be the kind of precursor of what was to come. But that wasn't quite the case. And so we followed, this is, of course, this is from the Frederick radar now. We'll go forward in time here. You can see those supercells are firing up there down to the southwest. I'll go forward here in time. You can see numerous discrete supercells there out in the open warm sector. We continued to try to get this showery activity to fire up along those horizontal convective rolls out in the open warm sector. But they seemed to be struggling, and we weren't quite sure why. We were expecting these showers to really kind of take off, but they were not doing so. But we turned our sights to these storms that were coming out of northwest Texas into southwest Oklahoma. And, of course, that Paducah storm produced the tornado there. The storm near Oklahoma City moved off north of the warm front, merged with the activity to the north of the warm front, and kind of fizzled out from there. And, of course, this supercell moved into southwest Oklahoma ahead of everything else, and it was kind of discrete and produced a significant tornado near the Mangum, Oklahoma area. You can see classic supercell there. You can see very well-defined hook echo right in there as well. Produced a significant tornado there near the Mangum area. And here's some footage of that. Formed very quickly, and you could just tell this could be our long track tornado of the day, as it was still discrete and it formed very, very rapidly. Take a look at the motion there. Very impressive motion there. This is from my friend Stephen Jones. Go check out his page, Tornado Intercept on YouTube, Storm Chaser Stephen Jones on Facebook. But pretty incredible footage there of this Mangum tornado, and it kind of quickly became a pretty stout tornado as it moved off toward the town of Mangum. But this was about it for the outbreak. As far as discrete supercell development in the open warm sector went, if we go back to our radar here, again, we started to really try to get those storms in the open warm sector. Let me go to the Frederick radar here. Might show it a little bit better. We go on with time. The Mangum storm continues, produces the tornado. And you can see we've kind of gotten more of a clustered sort of mode out here, not really any more discrete supercells to speak of, maybe some slightly discrete elements out here within kind of the main sort of broken line. But this mangum storm would move off toward the north and kind of merge with the line, and nothing out here in the open warm sector was really sustaining itself, and we were wondering why. And by this point, there wasn't really anything firing, so we kind of called the chase at this point. We were very perplexed as to why there were all these showers going up in the open warm sector, but nothing really was happening. And as we went on into the evening hours, just to kind of fill out the rest of the progression of the outbreak, this storm was of particular concern as it moved off into northwest Texas. There, it was still discrete, had a hook echo on it, didn't really do anything though. We also had some storms fire up well to the south along the dry line behind the initial batch of discrete storms there in northwest Texas. These formed along the actual dry line here, down toward the Midland, Odessa area. And we go on with time here, and these would fire up. The dry line would continue to retreat kind of out toward the west. Continued storm development out here. So this kind of was the area to watch here for the next couple of hours, as some of these storms produce tornadoes out here, given the favorable profiles that were still in place, it appeared. And these storms produced tornadoes. This was some footage here of a tornado near the Midland, Texas area, and pretty stout stovepipe there. So a pretty stout tornado down there with some of those discrete supercells. And this was the Dias Air Force Base near Abilene. This was the RAP sounding from 0Z down there. Of course, very, very, very favorable kinematic profile there. Some caps starting to build in, and we'll talk about that in a second, but a very unstable profile. Not enough convective inhibition to really inhibit these mature supercells from tornado genesis in a fairly well-mixed sort of boundary layer, 86/68 down there. So these storms were able to produce a few tornadoes here for the next couple of hours, as it was this storm near Midland. But then we kind of got everything to congeal into a line, and once again, the warm sector remained pretty dry for much of the rest of the event. We saw we didn't have anything fire up in the open warm sector aside from these showers here. I'll go forward in time as we go on through the evening hours. You can see not much going on. Some embedded supercells within the line here, but we eventually got pretty much just a line of storms to move through kind of in two batches. The initial batch of storms that was north of the warm front moved through Oklahoma, and then we had our second batch of storms that emanated from the activity in West Texas that actually produced some spin-up tornadoes here, one in the Norman area and one over near the Tulsa area. So all in all, it seemed like Oklahoma had dodged a bullet. The long track tornadic kind of discrete supercells had not materialized in the open warm sector. And so now let's go through a few reasons why that was the case. And the main reason why that was the case was the elevated mixed layer that was advecting off the Mexican plateau into the target area. So we'll go back to 700 millibars here. First, we'll go back to 500 millibars, kind of reset the scene here with our trough. So our trough was ejecting. Here you can see it across the Great Basin region. It was ejecting, but it was ejecting very slowly. We've talked about this before, how fast these sort of trough ridge pairs kind of move. When you have the distance from the axis of the trough to the axis of the ridge that is fairly sort of the size of the United States, it's not going to move a whole lot. But when your wavelength, your distance from the trough to the ridge axis is fairly small, it's going to move. And we're kind of right in the middle here. We don't really have a super tight sort of wavelength. This is a very large trough, very amplified trough. Small sort of ridge here. We do have a trough that was moving out into the Pacific Northwest, or excuse me, not the Pacific Northwest, the Northeast, that had kind of flattened the ridge. We think of the ridge kind of as being this sort of composite sort of thing in here. We can kind of say that the axis might be somewhere in there. So this is not going to move extremely, extremely fast here. And the slowness of the trough to eject actually allowed an elevated mixed layer that was residing across western Mexico, across the Mexican plateau, to advect its way northward along that strong low-level flow. If we go to 700 millibars, we can see it pretty clearly here. So I want you, this is at 18Z. I want you to take a look at these dashed red lines here. These are isotherms, or lines of equal temperature. And this is what we call a thermal ridge. So a ridge of warmer temperatures right across Texas into southwest Oklahoma. And this was kind of a semblance of that elevated mixed layer that was continuing to be advected off toward the north into the region. Usually, when you have the approach of the trough and enough surface heating, this will erode. But because that trough at 500 millibars was fairly slow to eject into the plains, it allowed the continued advection of this elevated mixed layer into the region. And this was extremely relevant for this event. If we take a look at our 21Z sounding here at Norman, you can see a very favorable profile, very unstable profile here, very nice looking photograph for a tornado, for lots of tornadic supercells here with long track, strong tornadoes possible. But watch what happens by 0Z, and keep your eyes here right around this little kink here, just above 700 millibars. I want you to watch what happens. Notice what happens. The cap strengthens, and we get this layer of steep lapse rates and kind of warmer, drier air to really place a stronghold on the kind of mid-levels of the atmosphere. Let's take a look at that again. Profile looks good, and by 0Z, that cap has strengthened there. So this is what was kind of choking off the storms in the open warm sector. We continue to get the showers to fire in the open warm sector, but as this cap continued to build in, it was not allowing those storms to mature. And if we take a look at some profiles here, so this is the 12Z wrap from Fort Sill, Oklahoma. So in southwest Oklahoma near the town of Lawton. And you can see the similar progression as to what we saw at Norman. Here we destabilized throughout the morning and early afternoon hours. By early afternoon, we were completely unstable. Lots of instability here with a greatly improving wind profile. We went through the afternoon, and notice what happens here. 18Z, we look pretty good, but notice right here, a little bit of elevated mixed layer, and keep your eye on that layer. Throughout the afternoon, that builds back in. By 21, 22, 23Z, that cap was very, very strong out around 700 millibars. It was prohibiting upward motion within that warm sector and was really stunting the growth of those showers in the open warm sector, despite a very unstable profile, 4,000 joules per kilogram of mixed layer CAPE, and a very, very favorable looking hodograph, wind profile for cyclic tornadic supercells here. And so it just shows it doesn't take much here to stunt warm sector development, because warm sector forcing by definition is usually fairly subtle. It's along these kind of subtle confluence bands or some subtle sort of embedded shortwave out in the open warm sector. And so the forcing is subtle, but sometimes if it's too subtle and you have this occurring, this kind of capping inversion that starts to build back in, that subtle forcing is not going to be enough to sustain development through that layer. And we saw that something similar on the May 3rd, 1999 event. If you recall our case study on that event, let me pull up the 0Z sounding from May 3rd, 99. Let me look at the observed soundings here. We'll look at the 0Z Norman sounding. And we noted that that cap was starting to build back in. Pretty strong layer of pretty strong elevated mixed layer there was building back in, but you had enough forcing in the open warm sector along horizontal convective rolls and confluence bands, a little bit stronger on May 3rd, 99, with a nice subtle shortwave moving through, that it was able to sustain mature supercells and produce tornadoes despite that little bit of elevated mixed layer building back in. So it appears that the forcing in the warm sector on May 20th, 2019 was just not quite strong enough to resist this strengthening inversion, strengthening elevated mixed layer in the mid-levels. Let's look at another profile here. We'll look at Purcell, Oklahoma, which is just south of the Oklahoma City metro area. Same progression here by early afternoon, completely destabilized, very strong looking wind profile. But notice what happens later on. This is at 23Z, very strong elevated mixed layer building its way back in. And again, the forcing in the warm sector was not quite strong enough, and you can really see it here at the Ardmore sounding. So far southern Oklahoma, still in the warm sector. Same sort of progression by early afternoon, destabilized, very strong wind profile. but we really get that cap to build back in by 23Z, and you can really see it here. It definitely cuts off and would serve to stunt the growth of those those showers in the open warm sector. So this was kind of the main reason that was keeping the warm sector and keeping this outbreak at bay. And the modeling from the night before was showing this building back in, but not to this extent. I want to show you here the 6Z wrap. So the overnight wrap model run, 6Z wrap, valid at Ardmore. And you can see what this is a really good example of it. This is our profile that the model was showing. Again, it's the 6Z wrap. So the 1 a.m. wrap model run on May 20th, valid for 18Z here on May 20th. So 1 p.m. On the afternoon of the outbreak. Once again, we see a fully destabilized profile, deep moist layer, very good looking photograph there. And you can see that the profile, we do get a little bit of that building back in, a little bit of that capping inversion building back in. But if we compare our Ardmore 23Z wrap sounding, our initialized sounding there, notice how much greater, how much more noticeable that capping inversion is here. And I'll go back and forth here. So this is the 23Z wrap initialization at Ardmore, really strong capping inversion. And notice that the modeling was not anywhere near that here across the region. So that was why models like the HRRR and these high resolution models were showing such a potent looking setup. And that's something like this is because the capping inversion that was forecast to build back in was not nearly as strong as it actually ended up being, due to the kind of slower advance of the main sort of trough and the allowance of that elevated mix layer to seep into the region from the Mexican plateau. And I want to bring to your attention here the April 27, 2011 outbreak, which was another kind of upper echelon sort of setup parameter space with kind of the same issues. This is at 18Z at Birmingham here. Notice the capping inversion. This was right as storms were starting to fire here across central Alabama into central Mississippi across the open warm sector. Notice the capping inversion there. You can see very strong capping inversion there at 18Z. But notice what happens by 0Z. By 0Z, that capping inversion is gone, and we were fully destabilized by 0Z, whereas in the May 20th case, we went from fully destabilized here, and that cap actually grew and increased with time there in the mid-levels. Of course, here, once again, Birmingham, we started off with capping, but as the afternoon went on, that capping decreased, and we were able to sustain supercells out in the open warm sector in the April 27th event. Another issue, not the main issue, but something that kind of goes along with that kind of the EML issue, were the overall lapse rates in the low levels. Let's take a look at the Norman sounding from 0Z. Notice the lapse rates here. Again, the lapse rate is that change in temperature as you go up in the atmosphere, and when you see something very steeply sloped line like we see kind of in here, that means the lapse rates are very steep, or the temperature is changing very rapidly with height. Notice here in the low levels that steepness is not that strong here. So the lapse rates, and you can see the 0 to 3 kilometer lapse rates, this first value here, 5.3 degrees Celsius per kilometer. We're trying to look for values generally above 6 degrees Celsius per kilometer, and the higher the lapse rate in the low levels, the more likely it is that parcels are going to be able to rise effectively and efficiently into the vertical, and would help them punch through this capping inversion that was increasing. Well, that wasn't the case here. Very weaker low-level lapse rates here were not allowing those parcels at the surface to really gain that upward momentum they needed to push through this capping inversion. And that was another sort of limiting factor going along with that increasing EML. And notice here at Birmingham for the April 27th event, our 0 to 3 kilometer lapse rates were much, much steeper in this layer. 0 to 3 lapse rates here, 8.8 degrees Celsius per kilometer. So very strong low-level instability here. Very steep lapse rates in the low levels were allowing these parcels near the surface for the April 27th event in the warm sector to punch through that cap, which was already decreasing with time, to sustain supercell development out there in the open warm sector. And we know what happened, of course, on April 27, 2011. So another issue that we ran into on the May 20th event were these storms to the north of the warm front that were continuing throughout the day. As we go on with time here, I'll move it forward a little bit with time. There's our Mangum supercell, just to kind of set the stage. That Mangum supercell producing that tornado out there. This is our elevated activity to the north of the warm front. And as we go through time here, watch this fine line that is emanating from these storms. You can see it in radar right in here. That was cold outflow that was surging southward from these northern storms, and that was helping to really reinforce the warm front and push it to the south, so that the air out in the warm sector across southwest Oklahoma was becoming increasingly pinched with time. So any of these storms, including this Mangum storm that would fire, were going to eventually run into this cold pool that was surging to the south that would stabilize the low levels and allow storms to become or remain elevated here. And if we go on with time here as well, you'll see that the Mangum storm, once it hits that outflow, here's the boundary. You can kind of extrapolate it out to there. Once it crosses that boundary, tornado threat pretty much ended with this storm, and it became outflow dominant very, very quickly. And so that was an issue with the southwest Oklahoma portion of the outbreak, and we can see on our surface map exactly what that outflow did. So this is at 18Z, 1 p.m., as storms were starting to fire here. Here's our warm front, somewhere in this vicinity right in here. And I want you to keep your eye on these observations right in here. 77 degrees, 77 over 68, 82 over 70 down here in southwest Oklahoma. But watch as we go through with time here. Notice as we go through with time, bam, as that outflow hits 51 over 51, 62 over 56. So by 0Z, that warm front, that outflow had pushed the warm front well to the south here and really allowed that front to surge south and that cold air to undercut any storms that were coming out of northwest Texas into southwest Oklahoma. So a number of issues were kind of plaguing this outbreak, thankfully for the people of northwest Texas into Oklahoma. Of course, that Mangum storm and the storm near Paducah and that eventual Mangum storm and that storm in central Oklahoma kind of happened in that sweet spot before that cap built in fully and before that outflow was surging off toward the south to undercut these storms. So these storms that produced the tornadoes were kind of in that sweet spot when the parameter space was still very, very good for long track tornadic supercells, but before that cap fully built in by 21, 22, 23Z to really choke off those storms and of course not allow that warm sector to go bananas. Another issue that may or may not have played a role was the wildfire smoke that was in the air. This is a satellite image from May 20th showing lots of wildfire smoke down in Mexico. There were plenty of fires burning down here. And when you have a southerly low-level jet that is bringing the air from the south toward the north into the region, it's going to push some of that wildfire smoke out into the target area. And that's exactly what happened across central Oklahoma into northwest Texas that day. I remember being out there, and you really could not see a thing unless you were right up next to the storm. And so visibility was very, very difficult. And there have been some hypotheses that have posited that the wildfire smoke, which sometimes serves to warm the atmosphere, may have played a role in the temperance of the overall outbreak. Although a few days later, May 23rd, 2019, it was another significant severe weather day for the Texas Panhandle into northwest Oklahoma. It was extremely hazy that day as well, and there was a wedge tornado near Canadian, Texas that moved toward Buffalo, Oklahoma in that haze as well. So not really sure what effect this haze, if any, had on the overall outbreak, but it is one hypothesis that is out there. But I think the main sort of takeaways here is this Mexican EML that built back in to the region was really tempering the overall threat for the region. You can see here, once again, it kind of builds back in that 10 and 12 degree isotherm there, just kind of sits over southwest Oklahoma and doesn't quite build back in. And one thing here before we wrap this up, this is a chart from John Davies. We've talked about John Davies' work before. He does a lot of great work on cold core events, as well as regular tornado events as well. And you can use, based on his work, 700 millibar temperatures to estimate areas that are too capped for thunderstorms. And kind of his threshold for May out in the low plains, so your Kansas, your central Kansas to central Oklahoma, western Oklahoma, down into north central Texas, is generally about 9 to 11 degrees. Anything above that becomes a little bit too warm for storms, too warm for those parcels to really push through that capping inversion. You can see that 10 to 12 degree gradient right in there across the target area. So again, that cap was building in with time and not allowing those warm sector storms to get going. So that's going to wrap things up here. This was one of the more interesting case studies that I have gone over. I think one of the more interesting ones for me, actually learning more about this outbreak and learning about the failure modes here. Of course, we know how well forecast this event was. Of course, high risk, 45 hashed tornado probabilities there across northwest Texas and southwest Oklahoma. Thankfully for the people in the risk areas here, it did not materialize thanks to that increasing elevated mixed layer off the Mexican plateau and kind of the weaker sort of low-level thermodynamics and that outflow surging from the north, undercutting the storms, all kind of played a role in mitigating the overall outbreak, the intensity of the outbreak across the region. So with that, thanks for watching. We will see you in the next video.